So in 2.7, the primary objective here is to show you a way to efficiently walk through a function, to walk through the derivative of a function so that we do not have to continually find or solve for each individual value of observation. So we have the same function, but before it was written as f prime of a, some constant is equal to, and then we had the limit h as it approaches 0, and everything's set up the same way. It's just that we were using a, which is a variable used for a constant. In this case, we're going to find that it's much more effective and efficient to simply solve our derivative from a function. So we'll take the derivative of the function f of x is equal to the square root x minus 1, and we'll solve it down as an equation for the tangent line so that we can plug our values into it, each one, and quickly find the slope of the curve at that particular point. And that way we don't have to go through the enormous work of finding the tangent line or slope of the curve at each point. We can do it once, and then we can take that equation and quickly find that tangent line for each individual point afterwards. So let's walk through that and see how it works. So we're still using, and the professor states that he typically uses this particular equation. I know the book has pointed out several ways that you can set this up. This I have found as well is the most effective way to find the derivative or take the derivative of a function. So let's go ahead and just walk through this. Our question is, take the derivative of the following. And what we're going to do is we're first going to find the equation for this function, find the derivative equation. So in the last videos in 2.6, I said that I have a bit of a process. The first thing is I usually find f of x, which we always know is just simply going to be the function. So f of x is equal to the square root of x minus 1. And then I find f of x plus h. Well, that just simply means put x plus h everywhere that x occurs in the original function. That's all it means. So we're going to take the square root. I'm going to write in my x plus h. So my x plus h minus 1. And that is going to be my f of x plus h. So let's go ahead and write that equation for the derivative. So we're going to say f prime, and this time we're just going to say f prime of x. We're not going to put the values in yet. And we're going to set that up as the limit of h is approaching 0. And we would set that up as f of x plus h minus f of x divided by, and the denominator is always h. And again, our goal is to eliminate or to reduce that h. That problem right now is that if we were to substitute 0 for h, of course we would have division by 0, and we can't do that. So that is the goal. That's the objective. So from here, we're going to substitute our function f of x plus h for what we just determined it was. So we are going to write the limit as h approaches 0. We'll put that function in, or replace the function f of x plus h with square root of x plus h minus 1. And we are subtracting just the function f of x, and we found that. We know what that is. That's just the original function, so we put that in. So that is x minus 1. And of course, this is still over h. So at this point, we have it set up, and we need to find a way to eliminate our problem, h, in the denominator. There's not much we can do with the denominator. There's no way to really manipulate this using the denominator, but we do have a way to manipulate the numerator, and that is using what's called the conjugate. So if I multiply by the conjugate of the numerator, or rationalizing the numerator is another way to express the same thing, I am simply rewriting the entire numerator, x plus h minus 1, and x minus 1. So those values stay the same. The only one that changes is in between here. We're going to put plus. And then, of course, to make sure that this is still an equivalent value fraction, I need to make sure that I multiply the numerator and denominator by that same expression. So we have x plus h minus 1 plus x minus 1, so square root. So we're now going to multiply through to each one of these in the numerator and denominator. When we do that, still bringing down the limit as h approaches 0. So when we multiply our first square root of x plus h minus 1 by square root of x plus h minus 1, well, the square roots go away, and we are simply left with the value, or the radicand, of x plus h minus 1. And then we are going to multiply, and I've said this several times in other videos, but this is also the same as taking the difference of squares. So if I changed each one of these to simply x minus, and let's just say that I had x minus 1 times x plus 1, we would end up with x squared, and then we'd end up with plus x minus x, and then in this case we'd have negative 1, where the middle values and the difference of squares always goes away. So in this case, what happens is that not only do the square roots go away, but we end up with a really nice numerator, whereby it is x minus 1. And then we can just simply move the denominator over so that we have h multiplied by the square root of x plus h minus 1 plus the square root of x minus 1. And we don't carry the h through. The reason we're not going to do that is because we're trying to reduce it. We're trying to find another h in the numerator that will allow us to eliminate that problem. We still have the same issue right now. If we put 0 or substitute 0 for h, that would be 0 times all of this, which would still be 0. So we still have that problem. We need to get rid of that h, and we're just about there. So the next step is to simply reduce like terms in the numerator. And to do that, we're going to carry this negative 1 through. I made sure to put parentheses around this set because I have not carried that negative sign through yet. So I'm going to rewrite this one more time so we can see what it looks like. As the limit h approaches 0, we still have x plus h minus 1. I carry that negative sign through to the x, I'll have negative x. I carry the negative sign through to negative 1, it becomes a positive 1. All of that still over h times square root of x plus h minus 1 plus square root of x minus 1. So let's go ahead and reduce those like terms. So we have a negative x and a positive x. We have a negative 1 and a positive 1. And we are left with a positive h and an h. So we have an h in the numerator and denominator. And finally, we were able to reduce our problem to simply 1 over 1. And that will leave us with the limit as h approaches 0 is now effectively 1 over the square root of x plus h plus 1 plus x minus 1. And now, if we substitute our h with a 0, we don't have a problem. So if I erase this h and I substitute with 0, and as soon as I substitute with 0, I can eliminate the limit as h approaches 0. So now we can just simply evaluate this as 1 over, well, square root of x plus 0 plus 1 leaves us with x, and sorry, that should have been minus 1. From here, I brought it down incorrectly. Apologize for that. So that would be x minus 1, so square root of, plus the square root of x minus 1. And of course, this can be reduced a little bit further. The square root of x minus 1 plus the square root of x minus 1. Well, those are the same. These are the same terms. So we can combine those, and we can call this an equation for the tangent line that is 1 over 2 times the square root of x minus 1. So now we've created the equation of the tangent line. And by doing that, we can solve for each one of those values. So let's go back up to the top. And we were asked to solve for f prime of 10, f prime of 10, of 17, and 5. Well, each one of those respectively are inputs along the function. We'll delete this. I will put I will just simply write our equation of the tangent line here. And it was 1 over, or divided by 2, times the square root of x minus 1. So let's go ahead and begin plugging in our values. So if we take f prime of 10, f prime of 10 is just simply going to be f prime of 10. And we will have 1 divided by 2 times the square root of 10 minus 1. And that becomes 1 over 2 times the square root of 9. And the square root of 9 is just simply 3. So that becomes 1 over 2 times 3. And that becomes just 1/6. And so now we can do that for any value that's in the domain, defined in the domain of the function that we're given. So as long as that value, the derivative, exists for the value that we're given, we can quickly find it using our equation of our tangent line. And that is essentially what 2.7 is all about. It's just showing you that this is how you can effectively find the derivative for any point along the domain of a function. So I hope that helps. Thanks for watching.